Welcome back to the Home Lab, and I've got another interesting build and demonstration for you today. What we're going to do is we're going to build some logic gates, that's AND, NOR, NOT, etc., but not using integrated circuits, but in fact using reed relays. Just before we start, again, I want to say a great thank you to all of you for watching, and also for PCBWay for sponsoring these videos and encouraging me to make all these bits and pieces. As you know, they do circuit boards, but they also do CNC machining and 3D printing, and they've got an absolutely excellent website where they share projects that other people have done. So why not go and have a look at that after this video, and you might get some ideas for your next project. Now, I'm sure you're all familiar with the 7400 series of TTL logic gates, and I've got literally hundreds of them. This is just a few in one of the boxes I've got. They were used in huge numbers in computers, certainly in the 1960s. Here's an example of a board from a DEC PDP-8, and you'll notice just how low the density is, with 3 chips on here that have a collection of NAND gates in them. And you'll also be familiar with how these chips work. I'm sure you've built circuits before. So here's an example of an AND gate working. So let's have a quick refresher on how logic gates work, and to do that I've got a 7408 IC here. That is an AND gate. So here are the inputs A and B, and there's the output, or some people call it Q. So what we'll do is we'll feed 0 and 0 in, and we get 0 out, so A and B are 0, and Q, the output, is 0. Let's have an input of 0, 1. So there we go, A is 0, B is 1, and the output Q is 0. Then we'll swap round and we'll have 1, 0, so A is 1, B is 0, and the output Q is 0. And finally, let's have 2 1s. So A and B are 1, and because it's an AND gate, if A and B are high, the output is high. So I thought it might be fun to go back to the days before there was TTL chips and digital logic. And so what we're going to do is build some logic gates out of reed relays. I'm also going to do a video where I build logic out of regular electromechanical relays. So before transistors were invented, computers needed another method of producing logical circuits, and one of the ways was to use a lot of switches and a lot of relays. So to demonstrate logic with reed relays, it was time to get building. I jotted down my initial ideas on paper and then grabbed my go-to material, which is A4 Perspex sheets. And after a lot of drilling and adding components, mainly reed switches and LEDs, and quite a bit of soldering too, I ended up with what I want to show you today. So let's look at the working of a reed relay. It's basically a physical switch that's operated by an external magnetic field. Tiny reed contacts in the glass container make, click together, or break, come apart in the presence of an external magnetic field. If you listen very closely, you can often hear a very faint click as this happens. It's not dissimilar in operation to a regular relay, where the magnetic field is produced not by a magnet that can move, but by a stationary electromagnet. Reed switches are used for all sorts of applications, but a simple one would be a magnet on a door and a reed switch on the door frame, making a circuit when the door is closed and breaking it open to perhaps set off an intruder alarm. So let me give you a quick tour of the board that I've built. So I've built the reed relay logic gates going down the board, and you can see buffer, inverter and NAND, etc. What I've also done is I've shown you the symbol for those gates, which I'm sure you're familiar with. And also I've used the Boolean notation. So A, not A and B, etc. So you can see how that's written down. Also, on the other side, I put the truth tables. So you should be familiar with these, but if not, I'll go through them. So what the inputs are, we'll call that A, and what the outputs are, we'll call that Q. And if we've got more than one input, we've got A and B, and we go through the counting in binary, so 0, 1, 2, 3 in decimal, as it were, and we see what the output Q is. The other thing I've done is I've got two little magnets here, and they're going to represent the inputs. So some of the relays here, or the gates, only have one input, so I'm only going to use a 0 when there is no magnet, and when I put the magnet in, that acts like a 1. So we can have the two different logic states on each read relay. So let's start off with the buffer. Now you might wonder what this is for. Well, it's good for separating logic circuits, but it's also really good if the incoming signal's not in a very good state. It will watch the voltage varying here, and if it reaches a certain level, we'll switch and square up the incoming voltage. So the truth table says that if we've got a 0 or a low voltage on the input, we get a low on the output, and if we've got a high on the input, typically 5 volts, we've got a high on the output. So currently we've got it set up so it is open, so there's no magnet here, so that's a 0. So we'll take a 1 and we'll bring our magnet in and position it on the read relay. The contact's now closed, so we've got a 1 on that, the presence of a magnetic field, and therefore the output is high. So now let's look at the inverter, a very useful device. So this is a NOT gate. So the output is not high when the input is high. So the truth table is reversed. In other words, a 0 on the input and a 1 on the output, and vice versa, a high on the input and a low on the output. So this uses a read relay that's normally closed, and what happens when we put the magnet by it is it opens and switches off this LED. So we've got a 0 on the input at the moment, we've got no magnet there, and we've got the output high. So let's bring in a 1, our magnet, and now with a 1 on the input, the output is low. Okay, so you're obviously getting the hang of this now, so we can have a look at the AND gate, and remember, when there's no magnet, that's a 0 on the input and a 0 on the input. So for the AND gate, for a 0 and a 0, the output is low. So the output, if you remember, is going to be high when A and B are high. So with a 0 and a 0, no output, Q is 0. With a 0 and a 1, the output is still low. With a 1 and a 0, the output is still low. And with a 1 and a 1, the output is high. So the building of the gates gets a little bit more tricky now with a NAND gate. So if you remember, a NAND gate is an AND gate with an inverter after it. It's a NOT AND. So it's the reverse of what an AND gate is. So in other words, 0, 0 is a 1, etc. until we get 1, 1, and then the output is low. So we've got a 0, no magnet, and no magnet. So the output is high. Let's have a 0 and a 1. And the output is still high. Let's have a 1 and a 0, and the output is still high. And now let's have a 1 and a 1 on the input. And it's tricky because these guys bounce together. Might have to hold them. Hold them down. There we go. And the output is low. So now let's have a look at the OR gate. So if you remember with the NAND gate, you can see if there's no magnet and no magnet, the two read relays are joined together. So the output goes high. But with the OR gate, I've used two read relays in parallel here that are normally open. So no signal can pass through if there's no magnet and no magnet. So 0, 0, if both inputs are low, the output is low. But you can see what happens when I close one of these. So if we have 0, 1, so I've now closed this relay, the output is high. If we have 1, 0, I've closed the top one, so the output is high, and these magnets are going to fly together, I think. But if I close both, the output will still remain high. So there is an OR gate. So we're on to the NOR gate now, and I hope you're finding this interesting, so we'll whiz through them. Only one left, the exclusive OR gate. So the NOR gate, there's the Boolean symbol for it, and the output is not high when A or B are high. So what I've got here is two normally closed read relays in series, and what I'm going to do is 0, 0, and the output is high. I'm going to put a 1 on this one, so we've got 0, 1, the output's low, 1, 0, this one will open up, the output is still low, and if both of them open up, you've guessed it, the output is still low. So that's the NOR gate with read relays. So finally, let's look at the exclusive OR gate, and it has this wonderful Boolean algebra symbol. So this is quite an interesting one. This is a special kind of read relay, and there's a changeover. Now, if you look at it now, we've got no magnet and no magnet. So this is connected to the bottom, and this one is connected to the bottom as well. So there is no through connection. So a 0 and a 0 means the output is low. But it's exclusively OR, so only if it's OR, not both. So let's have a 0 and a 1, and the output is high. Let's have a 1 and a 0, let's line it up properly, and the output is high. And finally, the really important part of the exclusive OR gate, it must have an output Q that is low if A and B are high. So let's get that in the right place. And there we go. A and B are high and the output Q is low. So that's the exclusive OR gate, and that's a quick look through a whole range of gates that can be built with read relays. So I do hope you enjoyed that video on read relay logic gates, and you'll have a look at the video I've made on logic gates made out of regular electromechanical relays. Anyway, as ever, thank you for joining me, and I'll be making another video very soon.